Okay guys, today we are going to talk about experimental design, and we are going to break down the different vocab terms that are commonly used in experimental design, what makes up a good experiment, and then later we're going to talk about cause and effect relationships. So first, define an experiment. An experiment imposes treatments on individuals to measure their responses. Imposes treatments on individuals to measure their responses. Okay, so I'm going to kind of talk about a potential experiment I could run as a teacher. And then we will reference it while talking about each of these terms. So let's say I want to do an experiment to see if studying really affects students' test scores. So on the next test, the Chapter 2 test, I'm going to randomly divide each of you. So I'm going to give you each, let's say there's 30 students in the class, each of you a number between 1 and 30. Maybe that is that it will go off the roster for this class. And then I'm going to randomly select 15 numbers, ignoring repeats. The first 15 numbers that are selected will be assigned to study 2 hours for the next test, and the remaining 15 numbers that are not selected will not study for the next test. I'm going to make sure that for the next test that I'm going to feed you all the same breakfast, tell you all to get 8 hours of sleep. I know that might seem like a stretch, but I'm going to encourage you to get 8 hours of sleep. I'm going to give everyone the same test, allow everyone to use a calculator, give everyone the same amount of time to take the test, and then in the end, I'm going to take the average of the two groups' test scores, the study group and the no study group, and compare the results. Okay? So, the next term, treatments. Treatments are what each individual in the experiment is assigned to do. Okay, so if you're referencing the example I just gave with the for the next test, the treatments in that experiment would be, there were two of them, studying for 2 hours and not studying for all. So those would be the two treatments in that experiment. The explanatory variable is what a researcher manipulates or changes in an experiment. So it's what a researcher or the researcher manipulates or changes in an experiment. So it's basically kind of just putting together your treatments, generalizing your treatments. So my explanatory variable for the example I gave would be study time, okay? The response variable is what we call the variable of interest. In the example I gave, what variable were we interested in my experiment? Well, we were interested in the test scores, okay? That's going to help us measure how well studying, how effective studying is in the example. So, qualities of a good experiment. First one is random assignment. So randomly assign treatments to individuals so neither treatment is given an advantage. Randomly assign treatments to individuals or individuals to treatments, either one works, so neither treatment is given an advantage. Okay, so notice in my experiment, I randomly assigned, I gave everyone a number and then randomly assigned them to groups, randomly picked 15 numbers to be in group 1. I believe I said that was going to be the group that was told to study for 2 hours. And the remaining students were in the no study group. If you just put the 15 students with the highest test score from for chapter 1 in one group and the 15 students with the lowest test score from chapter 1 in another group, you're not really, one group is truly given an advantage. You're not really randomly assigning. It's not going to be able to assess how well studying is truly affecting the test score, okay? Because you would have an outside factor, which is their previous knowledge or their chapter 1 test score, kind of affecting their results. So random assignment is always very important. Control. Control means to keep outside factors constant so we can identify exactly what is causing the response variable to change. So keep outside factors constant. So we can identify exactly what is causing the response variable to change. Okay, so in my example, I included multiple controls. First, I said I would give everyone the same test. That's controlling because depending on if I gave out different tests, that could obviously affect the test score. I gave everyone the same amount of time to take the test, told everyone they could use the calculator, encouraged everyone to get 8 hours of sleep. This way sleep wasn't a factor, and made sure everyone had a good breakfast, okay? Replication. You can replicate by either including a large enough number of trials or people to help balance out random chance or outliers. So include a large enough number of trials or people to help balance out random chance or outliers. Okay, so if I had 2 sections of this course, I'd probably want to use all 60 of my students rather than just 30, okay, because that really helps balance out random chance or any outliers. If there's students that just come to class a couple days a week, missing a lot of notes and whatnot, the more subjects I have in my experiment, it can help balance out any random chance or any outliers. Blinding. When we talk about blinding a subject is, so a subject is blind if they do not know which treatment they are receiving in the experiment. A subject is blind if they do not know which treatment they are receiving in the experiment. Okay, so in my example, the subjects were not blind because they can tell whether or not they're studying or they're not studying. Okay, they can tell that. In the medical field, an example where you could blind your subjects is if you were trying to test a new cholesterol drug on the market and you could make the cholesterol drugs look exactly the same. Okay, you could make the pills look exactly the same. Everyone knows they're taking a pill, but they have no idea if they're taking the new drug on the market or the old drug or like a sugar pill. Okay? So, something else I wanted to define is an observational study. Observational study is when data is collected by observing performances. In an observational study, there are no treatments and there is no control. Okay, so all the hypothesis tests we've been doing thus far, those are like observational studies. With the Carolina Panthers and trying to see if they're better at home or away, we weren't controlling for any outside factors. We weren't saying they were playing the same teams, they were playing the same players from their team, calling the same play. We weren't controlling for anything else. We were simply observing what was going on, collecting the data, and trying to make conclusions off of that. So no control, no treatment. So hypothesis testing, when we observe those performances, it's essentially an observational study. So can we determine cause and effect relationships from an observational study or from a hypothesis test? No. We can make conclusions, however, we cannot conclude cause and effect relationships. Now, what about from experiments? Can we make cause and effect relationships? Yes. In a properly conducted experiment, we can make conclusions and determine a cause and effect relationship. In a properly conducted experiment, so what do I mean by properly conducted experiment? Where we randomly assign, we replicate, and we have control. So in a properly conducted experiment, we can make conclusions and determine a cause and effect relationship. And we did that because we controlled for those outside factors. So we know it's not how much a person sleeps that's affecting their test score. We know it's not the fact that some students were given a different amount of time affecting it. We controlled for those. So we hold outside factors constant. We randomly assign and we replicate it. We do enough trials or have enough people included. We can conclude a cause and effect relationship. Okay? So let's practice this with an example. So it says, in baseball and football, you throw the ball with your left foot forward. Okay, so when you throw a ball, you throw it with your left foot forward if you are right-handed. However, in a game of darts, so if you kind of think about this, you guys, in a game of darts, players typically put their throwing foot forward. Tyler wonders if he has a greater ability to hit the bullseye when he has his throwing hand forward, so he designs an experiment to find out. He will throw 20 darts with his throwing foot forward and 20 darts with his opposite foot forward. I'm sorry, this should be foot. So he's trying to see which foot forward does he do better. Okay, so that should be foot. So formulate hypotheses. So what are we trying to test here? Well, our null hypothesis, remember, our null hypothesis is what do we always assume is true? Well, we're going to assume that Tyler has the same ability to hit the bullseye, because that's what he's talking about here. He wants to know his ability to hit the bullseye. Tyler has the same ability to hit the bullseye with his throwing foot forward and his opposite foot forward. Tyler has the same ability to hit the bullseye with his throwing foot forward and opposite foot forward. Okay, our alternate, what are we trying to prove? Well, we're trying to prove that Tyler has a greater ability to hit the bullseye with his throwing foot forward. Tyler has a greater ability to hit the bullseye with his throwing foot forward. Okay, so let's talk about the components of this experiment. Treatments. So what are we trying to test? Well, there'd be two here, two treatments. One would be the throwing foot being forward, and the other would be the opposite foot forward. Explanatory variable. What is the researcher manipulating or changing here? Well, they're changing the foot that is forward. Our response variable. Remember, our response variables are variable of interest. What are we interested in here? Well, we're interested in whether he hits the bullseye. Now, remember, randomization was one of our important key components for a good experiment. So how would we randomize here? Now, you wouldn't just want him to throw the first 20 darts with his throwing foot forward, because then he could get warmed up, therefore do better with the last 20, or he could become tired and do worse with the second 20. So it's important to incorporate randomization here. So we can do that by, now he's doing a total of 40 throws. So take 40 note cards, and we would label 20 with throwing foot and then the other 20 with opposite foot. Okay, now we would shuffle and pick a card. And this card determines how he throws next. Okay, so then you would do that until you run out of all 40 cards. Okay, so you just pick one off the top. If it's throwing foot, you throw with your throwing foot forward, record whether or not you got the bullseye, and then you'd pick another card if it's throwing foot again until you get rid of all 40 cards. So control. There's lots of options for things we could control for here. Control is pretty much anything you control for is a good thing. The only thing we couldn't control for here is which foot is forward, because that's what we're trying to test. Okay, so I was thinking some ideas I had for control, and yours might vary a little, but I was thinking you should control for the dart, the dartboard, your distance from the board, the technique you're using. You can always control for the clothing you're using, you know, whether you're doing this in a winter jacket or just doing this in a t-shirt, because that could affect your arm throwing or whatnot. Okay, so it's really hard to come up with a bad control. Like I said, the only really wrong one here would be which foot is forward, because that's what we're testing. Blinding. Can we be blind? Remember, we're not blindfolding anyone, especially when they're throwing darts. It's not about blinding, isn't about putting a blindfold on anyone. It's about whether or not the subject knows which treatment they're using or which treatment they're receiving. So can we blind Tyler in this situation? The answer would be no, because he can tell which foot is forward. Okay, now keep in mind, once the experiment is completed, we would compare results in the two contexts, okay? And after each trial, you guys, you would record the following. So just a little side note, record the following after each throw. So there's two important things that the researcher should be recording for this experiment. One is which foot was forward, or in other words, which foot was forward, the opposite or the throwing. And another would be whether or not they hit the bullseye. Now, we have one last page to kind of put this together and review hypothesis testing. We're going to say we actually ran this experiment with Tyler, and here's our results in this two-way table. Okay, so it says, what is the test statistic, the name and the value that we should use based on the results? Well, our test statistic here is going to be the difference in bullseye percentage. Now remember, it's important to tell us how you're subtracting. So we think, before we thought he was going to do better with the throwing foot forward. That's what we stated in our alternate hypothesis. So it would be the throwing foot minus the opposite foot. Okay, you can abbreviate that. So what is this difference? Okay, well, throwing foot, he was successful 6 out of 20 throws. Minus, because we're talking about difference. Difference means subtraction. For the opposite foot, he was only successful for 3 out of the 20 throws. So if we subtract those, we get a difference of 0.15 or 15%. So describe how to simulate the distribution of the test statistic, assuming you have the same ability with both feet. So remember, in a hypothesis test, We always go in assuming the null hypothesis is true. So assuming we have the same ability with both feet. Okay? So first thing we would need to do is take 40 note cards. So this is a review of what we've been doing so far this chapter. Take 40 note cards. Now we're going to label them. How many successes did he have? Or in this case, a success is a bullseye. Look back up to your two-way table to help you. He had 9 successes, so you're going to label 9 of them as bullseye and 31 as no bullseye. Then, with these note cards, you're going to shuffle and deal 2 piles. Now remember, one pile, you need 1 pile for each treatment, and our treatments were our throwing foot and opposite foot. Now he threw 20 with each, so there's going to be 20 in each pile. So 1 pile is going to be of 20, which is going to represent the results with the throwing foot forward. And the other pile is also going to have 20, and that's going to represent the results with the opposite foot forward. For each pile, you're going to find the bullseye percentage, and then you're going to subtract. So find the bullseye percentage for each pile and subtract. How are we subtracting? Go back up here. Remember, we thought he did better with his throwing foot forward, so we're going to subtract the throwing percentage minus the opposite foot forward percentage. And our last step in every simulation that we do in this class is always going to be repeat many times. Okay? So let's say that we actually did this, we went ahead and did this simulation in our applet. Sorry guys, on the printed copy my graph kind of got cut off, so I'm going to put my answer key up here. So here's the dot plot that shows 100 trials. Okay, so circle 100. Now remember, in order to find our p-value, we need our test statistic. So look back above. What was our test statistic? Our test statistic was the 0.15. So draw your line, find 0.15, which this is in terms of percentage, so that's 15%. So those dots right in between 10 and 20 look like they're right at 15. Remember, we count those. So I'm going to draw my line right there. We're going to see how likely it is to get that value and higher. Okay? So if you count up all those dots, you end up getting 26. Remember, there's a total of 100 trials. So that means there's 100 dots. So that gives us 26%. So I drew my line at my test statistic. And I use my test statistic to help me get my p-value. Okay? So there is a 26% chance of getting. Now, what do I write down? Use the label on your dot plot to help you. A simulated difference in bullseye percentage. And I do T minus O for throwing foot minus opposite foot. Of what value? Well, what was our test statistic? Where do we draw our line on the dot plot? We're talking percentage here, so I'm sorry, of 15% or higher by random chance. Okay, 15% or higher by random chance. So, based on the results of the simulation, what can we conclude? Remember, in our conclusions, we always compare our p-value to 5%. So our p-value here was the 26%. So since 26% is greater than 5%, So it's likely to happen by random chance. So since it's likely to happen by random chance, do we think that this is special enough? Do we think you actually have a greater ability with your throwing foot forward? No. So we do not have convincing evidence that Tyler has a greater ability to hit the bullseye with his throwing foot forward. Okay? Remember, you always reference the alternate hypothesis in your conclusions. So again, I'll read the conclusion one more time. Since 26% is greater than 5%, we do not have convincing evidence that Tyler has a greater ability to hit the bullseye with his throwing foot forward. And our last question here, you guys. Suppose Tyler actually did have a greater ability to hit the bullseye with his throwing foot forward. Could we say that his throwing foot was the cause of the difference in the ability that we had evidence for? Yes, because we went through, as long as it was a control, we controlled for outside factors and we ran through a properly conducted experiment, yes, we can conclude a cause and effect relationship, okay? And remember, that's what we did on the previous page. We ran through a well-designed, we designed this experiment, went through randomization, replication, control, okay? So yes, we can control, we had a properly conducted experiment, we can conclude a cause and effect relationship. Okay? Hopefully this helped you guys better understand experimental design. Good luck on your worksheet tonight.